Hello, everybody. Today we're going to be going over critical points in multiple variable calculus. Obviously, it is kind of interesting that I made this video before I made the Calculus 1 version of it, but, I'm just excited to make Calculus 3 videos, so why not? So, first things first, remember from Calculus 1, we're going to talk about relative extrema, critical points. Make sure you know all your definitions. What is a local minimum? What is a local maximum? What's an absolute minimum? And what's an absolute maximum? And we also have a new term called a saddle point. Okay, a saddle point is where, here, let's see. Okay, there we go. A saddle point is where the slope equals 0. So when the slope is equal to 0, but it's not a relative extrema of the function. And this can happen. For example, if you can, imagine like the center of a potato chip. It's not the peak of the potato chip. It's also not the lowest part of the potato chip, but it has 0 slope. So in 3 dimensions, we have things like that. We won't be dealing with saddle points today, though, for this problem. Okay. So let's say that we have this function z equals e to the negative x squared minus y squared. Let's find the relative extrema over the disk over x squared plus y squared is less than or equal to 1. Okay, so we don't need to worry about our specified disk until we get everything solved out. So let's just focus on our function first. So in calculus 1, you would take the derivative and set it equal to 0 to find the critical points. We're going to do basically the same thing, except we're going to be taking partial derivatives of both variables and then setting both of them equal to 0. So if we have the partial of z with respect to x is going to be, we're just going to keep the e to the negative x squared minus y squared, and we're going to bring down the derivative of this. In this case, the partial with respect to x. So it's just going to get negative 2x. And we're just going to have the same things here. X squared minus y squared. I know it looks a little ugly. And this should be equal to 0. We're going to set that equal to 0. Okay. And now let's do the partial with respect to y. Partial with respect to y is just the same thing, but with the y. E to the negative x squared minus y squared equal to 0. Now, you may be wondering, how are we going to find this out? I mean, we have 2 variables, and, we're setting them equal to 0, so how is this going to work? So, how this works is that if you think about it, e raised to anything, we're not going to get 0, so our only reserve is this 2x here. How do we make this entire thing equal to 0? Well, x has to be 0. X has to be 0, it's guaranteed, or it has to be approaching infinity. But we'll see why that's insignificant later. And in this case, y also has to equal 0 because e can't go to 0 because it's an exponential. So our critical point, in other words, is at 0, 0. Okay? So to classify what this critical point exactly is, what we have to do is we have to look at the matrix of second partial derivatives. You should have this in your notes. The matrix of second partial derivatives essentially says that the determinant of the matrix, hold on a moment, it's having some moments, the determinant is equal to, Okay, that's, my letters are a little bit too big. The second partial of f times the second partial of y minus the second partial of xy, otherwise known as the mixed partial derivative, squared. And the reason why it's squared and we're not just multiplying fxy times fyx is because for this specific function, since everything's continuous, as you learned from Unit 2, they are the same, in fact. So everything will be the same, so we just say it's squared, because when we deal with these type of problems, we're going to have smooth surfaces, not jagged and discontinuous surfaces. That's not what we're dealing with here. So we're just going to simplify it down to this. So for this next portion, we just have to now find the second partial derivative of z. So we found out that the first partial derivative with respect to x was negative 2x e to the negative x squared minus y squared. So all we now need to do is we just need to use the product rule. Use the product rule and say that f of, hold on a second, gotta get the f xx, the second partial with respect to x, is equal to negative 2 e to the negative x squared minus y squared plus 4x squared e to the negative x squared y squared minus y squared, sorry. And you can find that on your own as well, but I just did it simply. You'll just use the product rule. So that's the same thing as 2x squared minus 1, 2 times 2x squared minus 1 times e to the negative x squared minus y squared. Okay. And for the partial with respect to y, it's going to be the exact same thing, but with y instead, because everything is the same. So it's just going to be 2 times 2y squared minus 1 e to the negative x squared minus y squared. Okay. So everything there is good. You could check that for yourself. Now let's find the mixed partial, fxy. So we have to look at x. So we're looking at our partial derivative with respect to x, and then we're taking the derivative with respect to y. So what we're going to get is we're going to bring down the derivative of the top. So we're bringing down a negative 2y, in other words. So you get 4xy e to the negative x squared minus y squared. Okay. So now let's just chuck this all inside the determinant. Simply, we'll just, let's go down, extend the page a bit. And when we do this, we essentially are saying that our 2 times 2x squared minus 1 e to the negative x squared minus y squared times this expression here, our second partial with respect to y, right here, negative x squared minus y squared minus 4xy e to the negative x squared minus y squared, and this is all squared. So in other words, we're multiplying the top by 2. Okay? So what we're going to do is we're just going to simplify. We're just going to simplify things out. So the determinant, in other words, you can simplify this for yourself, but since I don't want to waste too much time and space, I'll just say that the determinant at any point is equal to negative 4 times 2x squared plus 2y squared minus 1 times e raised to the negative 2x squared minus 2y squared. Okay, it's pretty simple to find, but you can do that for yourself. So for x equals 0 and y equals 0, because remember that is our critical point, the value of d, our determinant, at 0, 0, is equal to negative 4 times negative 1 times, if we plug in 0 for x and y, we get e to the 0th, which is just 1. So this is going to be equal to 4. 4 is in fact greater than 0. Okay? 4 is in fact greater than 0. And if we plug this in, if we use the second partial derivative with respect to x, and we also plug in our point, okay? And if we plug in our point, then we get that our partial of z with respect to x squared is equal to negative 2. This is less than 0. So what this says is z essentially has a local maximum at 0, 0. Okay? And if we just evaluate the function up here at 0, 0, you're just going to get 1, because e to the 0th is equal to 1. So, i.e. a local max at 0, 0, 1. Okay? So, next thing, we have to classify, we also have to try to find the minimum as well. And our minimum is what's going to be bound by our disk. So coming back from earlier, we were talking about how we're taking it over x squared plus y squared is less than 1. That is our disk that's going to, be the basis for our minimum. So now all we do is that we essentially are just use the equals part of the disk. The greater than or equal to symbol is not very relevant. We don't need to abide by it. We'll just use the equal to sign. So over x squared plus y squared equals 1. Remember here that we have z equals e to the negative x squared minus y squared. And essentially, this is also equivalent to e to the negative x squared plus y squared. And according to this, x squared plus y squared equals 1, so we can just substitute it right in. So e raised to the negative first power, which is approximately 0.37 if you type it into your calculator. So this means that there's a absolute maximum, or sorry, not minimum, absolute minimum at 0, 0, 0 point, or 0, there's an absolute minimum at 0, 0, 0.37, and since we're talking about, so the surface and our max is not bounded by the surface, our absolute max is also at 0, 0, 1. All right, so we've solved this problem. Let's do a quick overview, and then I'll show you a graphical representation so you can take this all in. So, the first step in solving for the critical points, or the relative extrema, the first step is to take the first partial derivatives with respect to x and y, and then we set them equal to 0 because the slope of the tangent plane is 0 at the relative minimum or maximum. Then we just solve for the x and y values that make, them 0. And those are the critical points. So then, now you take the second partial derivative. After that, you take the second partial derivative with respect to x, y, and the mixed with respect to x and y and x. So then you evaluate the derivatives at each critical point. So when you evaluate d is going to be equal to the determinant of the matrix of second partial derivatives, and then you evaluate that determinant at that pair. And that'll tell you, and that'll classify each critical point. So if the determinant's greater than 0 and the determinant, or in the second partial derivative with respect to x is greater than 0, then that point is a local minimum. But if the determinant's greater than 0 and the second partial derivative with respect to x is less than 0, then it's a maximum. And of course, if d is less than 0, then it's a saddle point, but we didn't talk about that in this video. And of course, if d equals 0, then we have to use we have to have more information to classify this point. So now all we have to do after that, and what we ended up doing is we classified, or we did not classify, we evaluated the function at each critical point, trying to, find the relative minima or maxima. And then to find the absolute extrema over a specified region, we talked about our absolute has to do with the specified region that we're talking about. To find the extreme values, we just plug in in this case, our little equation, x squared plus y squared equals 1. Okay. So that is how we can find the critical points of functions over another function in 3 dimensions with multiple variables. Now, I want to show you how this looks graphically. So, obviously, I'm not the best artist, so it will look a little weird. However, all I'm saying is that e raised to the negative x squared minus y squared looks something like just a plane of just a flat plane, except there's a little hump in the middle. It looks kind of similar to a function like this. It looks similar to e to the negative x squared, right? Just in multiple dimensions. Okay. It looks kind of like that. And all this is saying is that over this disk, this e to the negative x squared, its absolute minimum where it intersects with this little disk thing here, and in this case it's like a little cylinder. And we're only talking about this part specifically, but we're essentially just talking about a little disk and then a little hump over that disk. We're generally talking about this little 3D semicircle. Okay. And all it's saying is that we have this minimum here. This is 0, 0, 0.37, and it's essentially saying that this maximum here is 0, 0, 1. This is all this is saying. So it's essentially saying that the disk bounds this function between these two relative extrema. Anyway, hope you like this video. It's took a very long time, obviously, to make, so I'd appreciate it if you like and subscribe, and I'll also be taking suggestions in the comments for future videos. I can do anything from basic math to calculus 4, so I hope to see some suggestions in the comments, and goodbye.